You are now familiar with one semiconductor component, the diode. However, the transistor is where electronics really gets going. It is an active component, and is therefore used in many control units in motor vehicles. In this section, you will find out how transistors are made and how they work. You will find out how they are used as amplifiers and electronic switches. Finally, we will introduce field effect transistors. These have numerous advantages, which is why this type of transistor is the one most often used in motor vehicles. The transistor consists of three differently doped crystal regions, in this case, two N-type regions and a P-type region. A depletion region forms between them due to the diffusion and recombination of charge carriers. It can also be done the other way round. Start with an N-doped crystal and click two areas in it to create P-type regions. Depending on the regions they contain, the components are called either NPN transistors or PNP transistors. Depletion regions form at the two junctions between the regions. These transistors are therefore known as bipolar transistors. The middle region is called the base. The two outer regions are differently doped. The lightly doped region is called the collector. The more heavily doped region is called the emitter. The symbol for a transistor shows the base as a bar and the collector and emitter as two diagonal lines emerging from it. There are different symbols for NPN and PNP transistors. On NPN transistors, the arrow on the emitter points away from the base. On PNP transistors, the arrow on the emitter points towards the base. Click the link for more information on the different types of transistor. Transistors are mainly used as amplifiers, for example, to increase the current of a signal at a given voltage, or to amplify the signal voltage at a given signal current, or to amplify both the signal current and the signal voltage. Depending on the application, one connection is used as the signal input, another is used as the signal output, and the third is a common reference point for the signals. Transistors are mostly found in the emitter circuit shown here, where the emitter is earthed. The collector base path and the emitter base path are opposing diode paths. No current can flow between the collector and the emitter, whatever the polarity, because a depletion region is always present. But what happens if current is applied to the base? Connect the input circuit by clicking the switch. With this polarity, the lower depletion region disappears and electrons flow from the emitter to the base. Note that the physical current direction is the opposite of the conventional current direction. Electrons also flood the upper depletion region. Now enough charge carriers are available for electrons to flow from the emitter to the collector as well. This current is about 100 times higher than the base current. This is what the amplifying effect of a transistor is based on. A transistor is a current-controlled amplifier because it needs a base current to generate the higher collector current. Drag the speaker connection to the transistor connections and listen to the difference. This kind of transistor Transistors can also be used as electronic switches. In this example, the fan should be switched on in bright sunshine. Shine light on the photoelectric cell by moving the cloud away from the sun. The transistor amplifies the very low control current from the photoelectric cell and switches on the higher load current of the motor. You can also move the cloud back again. Think about the state of the fan control circuit in each case. Does base current flow? Does collector current flow? What is the voltage at the collector in each case? What is the voltage at the motor? The transistor acts as a switch here, similar to a relay. However, the transistor switches faster, silently, without wear, and with much lower control current. Click the link for a detailed description of the transistor switching states. Have you ever wondered why control units sometimes have heat sinks? This transistor controls a fan motor. First look at the transistor when it is not conducting. The entire supply voltage is across the transistor, but no current is flowing. The loss is the current multiplied by the voltage, so in this case it is 0 watts. Now click the variable resistor to switch on the fan. The transistor is conducting, and the electric fan motor generates a current of 40 amps. The loss in the transistor is now 28 watts. This loss is converted to heat, which must be dissipated via the heat sink. Now we want to run the fan at half speed. One way would be to reduce the base current, so that the current and the voltage at the electric motor would only be half as high. In other words, 20 amps and 6.5 volts. What would be the loss at the transistor? Click the right value. One might think so, but it's wrong. Check the result against the equation. At 20 amps, the voltage is divided. 6.5 volts are across the fan motor, which of course runs slower, and another 6.5 volts are across the transistor. In this case, the loss in the transistor is 130 watts. This is much more than in either end position, which makes this circuit impractical. To prevent high losses, most consumers in a motor vehicle are only switched either on or off. Take a look at the interior lighting. Where intermediate states are required, for example, dimming, the circuit switches rapidly between the on and off states. This is called pulse width modulation. However, this happens so fast that it is imperceptible to the human eye. The lamp appears to glow steadily. The ratio of the on and off times determines the average power of the load. Try it out yourself by clicking the buttons on the electronic control unit. Click the link to find out about other applications of pulse width modulation. A more sophisticated development of the bipolar transistor is the field effect transistor. There are many variations, but we will deal with the protected insulated gate field effect transistor because it is not only used as a single component, but is also the basis for integrated circuits. Its component parts are applied on a p-type substrate, whose upper layers are lightly doped and lower layers more heavily doped. Two n-type regions with electrical connections are added. These are called the source and the drain. Depletion regions form where the p-type and n-type regions meet. The source, drain and substrate all have electrical connections. Above the separating p-type region there is another electrical connection, known as the gate. However, this has no contact to the p-type region. Instead, it is insulated by a layer of quartz. Thus, the gate merely acts like a capacitor plate. The symbol shows the four connections of the field effect transistor described here. You can find more symbols in the glossary. If there is no voltage between the gate and the source, the depletion regions prevent current from flowing between the source and the drain. The field effect transistor is off, and no current flows in the circuit. Now apply positive voltage to the gate. To do this, keep clicking the up arrow on the adjustable voltage source, and watch what happens to the semiconductor. The positive electrical field of the gate and the drain displaces positively charged holes from the p-type region and pushes them inside the crystal. At the same time, it attracts electrons from the two n-type regions. The n-type regions expand. Once a certain threshold voltage is exceeded, the two n-type regions meet. Now current can flow, and the wider the channel, the greater the current flow. The source drain path acts like a variable resistor. In the conducting state, the resistance is only about 10 milliohms. Despite this, no current flows in the gate, because it is electrically insulated. This means the field effect transistors can only be controlled by voltage. Try it out. Click the link to find out more about how field effect transistors work. Do you remember? A bipolar transistor is controlled by the base current and can amplify it around 100 times. Therefore, if you want to raise the control signal of a microprocessor, typically 2 milliamps, to that of an injector, typically 20 amps, you need two amplifier stages. Field effect transistors, especially power MOSFET types, can do this in one stage. The advantage is that the source-drain path is controlled exclusively by the gate voltage, with no current. This means no control power is needed, which makes the circuitry of control units much simpler. In practice, therefore, the power outputs of control units are equipped with field effect transistors. However, this advantage can become a problem when we look instead at the inputs of the control units, not the outputs. Because the gate is insulated, it only takes a slight electrostatic discharge to cause flashover between the gate and the semiconductor, leading to irreparable damage. With a bipolar transistor, the discharge is safely conducted through the base emitter path. Transistors, like resistors, capacitors and diodes, are discrete components and are therefore still very important. However, electronics really took off with the invention of integrated circuits, where multiple discrete components are placed on a single semiconductor crystal known as a chip.